Okay. It's my great pleasure to introduce Gaetan Borot from Max Planck Institute. And I think there's a shuffle or some small some communication of the title here. So that's it now.
Okay. So I can also give an alternative title, which is Knots not in S3.
What?
Knots not in S3. Okay. So I thank the organizers and also our host of the Confucius Institute to provide us this very pleasant environment for a geometry conference. And I want to talk about knot invariants for knots, which are not in S3, but in other simple manifolds, which are Seifert manifolds. So you already know that if you have a knot or a link in S3, you can define a Jones polynomial as a Laurent polynomial in Q. More generally, we heard I've already introduced many things. So if you have any compact Lie group and a representation, you can define some VRG, which will be Laurent polynomial in Q and Q to the n, where n here is the rank of the group G. And actually, depending on the type of group you study, so I want to consider typically either SU series, the A series, or maybe SO or SP series. In that case, for SU, you get what's called the HOMFLY polynomials. So this is in Z, something like that. And depending on the type of group, maybe there's an integer here, which would just be 1 for the SU series, but maybe some 2s for this one. Okay. So for SU, that's called the HOMFLY.
Plus minus.
Plus minus, of course, it's Laurent polynomial. So here that's the colored HOMFLY, and here that's the colored Kaufman polynomial. And if you take R, which is just the fundamental representation, then you indeed get what's called the HOMFLY PT polynomial, that's for SU, and you get the Kaufman polynomial for SO or SP. Sorry, I think it's good. So that's for knots or links in S3. If you want to study knots and links in some other free manifold, then the story is different. You do not have anymore this possibility. You can do, as Tom was describing, you can define those VRG for certain manifolds. The first option is to define them in a Hadiro array. That's one possibility. The other one, which is more in the spirit of Witten's proposal in the 90s and studying these knot invariants by quantum field theory, is to do that with Chern Simons theory. So Chern Simons theory is a quantum field theory defined by some path integral, which is mathematically not well defined. Sometimes you can compute something exactly, most of the time no. But what you can always define rigorously from the path integral is doing perturbative expansion. So by setting Q, which is exponential of h bar, and sending h bar goes to 0.
Exponential of h.
And, sorry?
It's really exponential of h.
And choosing a flat connection, you can expand the path integral around this flat connection and define those VRG as formal series in h bar, which are also formal series in U, where U is n times h bar, and n was the rank of the gauge group. G. And this is what I want to consider here. So one way to, the mathematical framework for that is that the Chern Simons partition function can be defined as a perturbative series in h bar for n3, a closed free manifold. And let's say for the SU series, you can define a partition function like this, using the theory of LMO invariants. So LMO invariants, when you apply a wave system, which is defined by the gauge group, you can define some numerical invariants Fg, which mean not numerical, but which are formal series. And if you do that for SO and SP, the only difference is that here the grading might be different, and you rather have sum or G, which could be a half integer, and to the 2 minus 2G. Okay. So that's for closed manifolds, and that, in a sense, captured the expansion, the perturbative expansion of the Chern Simons partition function close to the trivial flat connection. Yes.
Do you want it really to be a rational homology sphere?
Sorry?
Do you want it to be a rational homology?
For example, yes. So in some other cases, there are also ways to evaluate the Chern Simons partition function in a finite dimensional integral, and in that case, you can give also a sense to that. So LMO, I agree, applies only to rational homology spheres. And if you have a link, then you can, in rational homology spheres, you can define VRG, again, as a perturbative series using the conservation table. In that case, it's more convenient to use, so for any representation of G, you have this VRG. So you can work for any, you can extend that by linearity. So for any element in the representation ring of your group, you can associate a not invariant, which is a formal series. And instead of working on the basis of irreducible representations, so which is just, so this representation ring is just a ring of symmetric functions. So this is just due to the Schur polynomials. I prefer to work in the basis of, so it's a virtual representation in the basis of power signs. So instead of VRG, I will define some omega bar k, depending on M1 and k, which is associated not invariant and also depend on G. And I also want to introduce omega k, which would be, that would be the connected observables, and that would be the disconnected observables. So for example, if you have just two of them, that's the kind of covariance of two things. So that's connected observables. So from this series of perturbative invariants, if you do that for SU, you find out that omega k has the following form. And to the 2 minus 2g minus k, omega kg, m1 and k, that's for SU. And if you do that for SO or SP, you just destroy the grading, and that can become a half integer. And there would be different invariants for SO. Okay. So I want to compute for certain class of sphere manifolds and a certain class of knots in those sphere manifolds, those omega kg.
Is exponential missing?
Where? Here? No.
In front of the sum.
No, there is no exponential. It's only in the partition function. These are observables. So expectation values.
Excuse me, so M1 and K, it's a partition, right?
It parameterizes the partition. It's the length of the parts of the partition. So these things contain all the information about the perturbative series VRG for all R's. If you want R's which are described by a Young tableau with less than k rows, you need to know all the omega k prime j where k prime is smaller than k. So this is an equivalent way to reformulate the information, but which emphasizes the grading here. So that's an equality of formal series in this way. Okay, so that's for the thing I want to study. Now I have to tell you in which manifolds I want to consider that.
And where are the flat connections that we encoded?
Sorry?
Where
Oh, I just choose a flat connection.
We choose one.
A trivial flat connection.
The trivial.
The LMO invariance and continuity integral have to do with a trivial flat connection.
Right.
So the three manifolds I want to consider are the Seifert fiber spaces. So it's the simplest class of three manifolds if you go away from the three sphere. To define them, I need to say what is a standard fiber torus. So you take a solid torus. Maybe I will write it that way. So you have a central fiber and the peripheral fibers. And here you will glue that together, but with a rotation of angle 2I pi d over A, where B and A are cocoon. So this will just glue to itself, but that one may glue to that one. So this is called the standard fiber torus. And now a Seifert fiber space is a manifold M3 which has a partition in circles, so that every fiber has a neighborhood which is a standard fiber torus for some B and A. So S1 fiber has a neighborhood which is a standard fiber torus. So the basic fact about Seifert fiber space is that there exists only a finite number of fibers which have a neighborhood where A is not equal to 1.
What is?
Sorry?
What do you mean by fiber? The fiber of the S1?
S1. It's a partition in S1. Just take an S1. It has a neighborhood which is a solid torus of this type.
So if you, so is it vibration? I mean, is it the way you describe
no, it can be singular.
Yeah.
It can be singular. So precisely the exceptional fiber is the one where you have a non-trivial rotation here. So these Seifert spaces have a nice classification. Here I only want to consider the ones which are oriented and whose orbit space. So you identify 2 points on the same fiber is a sphere. So in the classification you have a certain number of geometric invariants of the Seifert spaces. The first one are the orders of the exceptional fibers, A1, AK. So this order of exceptional fibers. Then you can represent, so here I actually have a sphere, so that's the orbit space. And you have some points which are associated with exceptional fibers. So topologically this is a sphere, but actually these are orbifold points in this fibration. So it's a fibration over an orbifold. In particular, this you can compute its orbifold Euler characteristics. And this is 2 minus, I should call that R, the number of exceptional fiber, 2 minus R plus sum from n equals 1 to R of 1 over AM. And this will play an important role in the following. You have also another invariant, which I will call sigma, which is sum of Bm over Am. So the Bm's were those, this numerator of the rotation, co-prime with A. But actually these fibers, exceptional fibers, sit in the ambient manifold in some way, so you have some freedom. And this freedom is represented by another integer. There are many ways to represent a Seifert fiber space with some B's and this B, but this is an invariant of Seifert fiber spaces. Two isomorphic one have the same sigma.
The square bracket is?
It's just a bracket, you can forget it.
It's not the Gauss bracket.
It's the simplest thing you can imagine. So in those Seifert fiber spaces, the pi 1 is not trivial. So you have some generators of the pi 1. So unlike in the three sphere you have the knot, and then all the other knots are non-trivial. In the Seifert fiber spaces, you have many unknots. which correspond to the representative of generators of the pi1. So those I will call the basic knots. And the basic knots here, you can represent them as knots along the exceptional fibers. So you have KA1, KA1. So these are the basic knots. If you want to know, if you take now any link in a Seifert fiber space, you can always, so this construction of a perturbative invariance, you can always write down scaling relations for them. You just expand the weight. Each way there was Q in the scaling relation, just expand Q in powers of H bar, and so on. So if you know the value for the basic knots, by scaling relations you can define what is those perturbative invariants for any link in the Seifert fiber spaces. So if one knows the VRG for basic knots, then using scaling, you know it for any link.
You only need these R, not an extra true unknot for the generic fiber.
Oh.
Kind of the K0.
Well, the true unknots,
Well,
you can
in the
take it
case
to
of the
be
sphere, R would be 0, and so this would be empty set, but that wouldn't be enough. You would need the unknot. So I'm
I
asking,
think the
don't you
unknots-
need the true unknot as well as these basic knots?
I think the true unknot is also normalized as is in a usual case, as in a 3 sphere.
But you
I
still
would
need
say.
it, so you have to fix it in some way, or not?
Yes, but its value, so the difference that the value for the unknot, I think it is known, and I would say it's the same as in a 3 sphere, but the values of this VRG for the basic knots, they have some value by the Kontsevich integral, which are a priori unknown.
Okay. So if you have connected some of these two basic knots, how can you calculate them? I mean,
How can you do what?
I mean,
Next one.
the scaling relation is
Mhm.
probably not enough to do the connection of these two basic.
So let's say that I take from a paper of Calfagiani, where she said that if you know the values for the basic knots, then you can define for all lengths these invariants.
Yeah, but the basic knots are elements of the fundamental group.
Are representatives of the pi1, yes.
Yeah, but they are more than just these. Just this. The fundamental group is infinite, and here you have only a finite number.
It need not be always infinite.
Well, but certainly more than this. I mean, it's actually infinite except for.
I think you just need, representative of generators of the pi1, not for all elements of the pi1.
No, you need all elements of pi1, not just.
They might be related, but the relation is not known and complicated.
No, they are conjugacy classes.
The
So
countries, you need
a
the
basic knot.
one
Every
for
conjugacy class is represented by a knot, and you need one for every conjugacy class in general.
because they're the same as the homotopopacity. Free homotopopacity.
Okay. So plus, so basic knot plus. So if I call that basic knot plus, what? Let's put it. Okay. So now I want to present the main results. So it's as follows. So theorem 1, for all Seifert spaces which have pi or positive, say for the SU case first, the omega kj are computed by the topological recursion of Eynard and Orantin for an algebraic spectral curve. So P of exponential x exponential y equals 0, well, this is a polynomial depending on this data. And that I use as a finite list. And of course that should depend on mu, which is n times h bar. If you do SO or SP, then the omega kg, where now g is a half integer, They're computed by, so not topological recursion, because you have this, you destroy the topological grading, but by a similar residue formula. The one that appeared in the talk of Bertrand. For the spectral curve, so if I call that P of SU of X, Y, and U, for SO, you just rescale the variable U by U over 2. And moreover, the geometry of the initial manifold reflects in the geometry of the spectral curve. So now I will write the table. And I will just concentrate on chi orb strictly positive. And in that case, the complexity is just given by quotients of the 3 sphere, by a finite group of isometries. So the first thing we divide by a cyclic group. This isometric group of the 3 sphere, they have an ADE classification. So we'll just write in the ADE label. So here, I will write the order of exceptional fibers. Here I will write the degree of X in P, the degree of Y in P. I write the genus, so maybe I should write capital G, the genus. And on top of that, so here you have quotient of the 3 sphere by some AD subgroup. On top of that, this curve comes with an action of a Weil group of a finite root system on its various sheets. So these curves, P of xy equals 0, it covers P1. And so these are several sheets. And the sheets have an action of a Weil group of finite root system. So now I will write the list. So those ones are the best known is the length spaces. In that case, you take 2 exceptional fibers. The degree in X is A1 times A2. It's A1 minus, it's A1 plus A2. The genus is A1 minus 1 times A2 minus 1. And the Weil group is that one. So now you look at this prismatic variety where you divide by dihedral groups. So here, this is 2 P, 3 exceptional fibers. And you have to distinguish if P is even or if P is odd. So if P is odd, the degree of X is 4P. You have 2 times P plus 1. The genus is 2P plus 1. And the Weil group acting on the sheets of this curve is dP plus 1. So that is dP plus 2 in the AD classification. Whereas here, this is 2P, P plus 1, the genus is 0, it's a rational curve, and you have an action of AP.
And the dot you're taking is all the exceptional fibers, right?
Sorry? It's all the data of all exceptional fibers.
Yeah. And they get labeled by different labels, right?
Yes.
Yeah. But is the polynomial uniform in all the labels or no?
What do you mean uniform?
What?
The polynomial does not depend on which fiber you choose. There's one spectral curve from which you can obtain all invariants of basic knots.
With all possible labels of the central fibers.
Of which variable?
Well, there's the labels, there's the representations that you want to attest.
Yes. So that's what I was saying. When you will compute omega kj of this spectral curve with some extra initial data,
Yeah.
when you expand that when x goes to infinity, you would read the coefficients. And if you do that for any k, in omega 1, etc., up to omega kg, you would be able to recognize and to read the coefficient of expansion of VRG, where R has a length smaller than k.
Do you know what the polynomial is explicitly?
So I will say a word about that. So there are three exceptional cases which are related to the tetrahedral symmetry group.
I mean, the group is not E6, E7.
No. The group is not. No. It's the label in the classification of finite isometry subgroups of S3.
Exactly.
So this is the binary. These are all binary polyhedral group. So the tetrahedral one, the octahedral one.
It's really not ADE. It's really Plato.
Yes.
It's earlier.
And the icosahedral one. And that manifold is actually the Poincare sphere. So in that case, you find a curve of degree 8 and 8, which has genus 5 and an action of D4. Here you find a curve of degree 36, 27, and genus 46, and an action of E6. And here you have 540, 240, genus 1471, and an action of E8. What you can notice.
And what are the AIs?
Sorry?
What are
Oh,
the
the AI says 2, 2, 3. 2, 3, 3, 2, 3, 4,
Yeah.
and 2, 3, 5.
I knew that. Yeah.
And the Plato symbols. So what you can notice here, of course, these A's are not the same as those ones. Here I'm really speaking about the Weil group of this root system. Here this is a AD label of an isometry group of S3. What you can notice is still that this thing is, the AD label is smaller or equal to what you observe here. There's only equality for E8 and I think for the length spaces.
So maybe you said that this table describes the full list of Seifert fiber.
For chi-orb strictly positive and orbit space, which is a sphere. So the only case where so we know a lot about those curves, we do not know the expression, the full expression in every case. We know the full expression for this one and this one. And for all the others, we know what is the ramification data, we know what's the Newton polygon, we know the coefficient on the boundary of Newton polygon, and we know that the coefficient inside the Newton polygon satisfy some algebraic constraints. And we can write. It just should match the correct genus and have the correct ramification data. But solving those algebraic constraints is quite formidable. So I think I have it, but it was not checked numerically yet for here. And the coefficient inside, you can express it in only one number, which satisfy, as a function of u, a degree 25 equation. So if this is already for E6, if you want to do that for the Poincare sphere, which is the most appealing, it seems out of reach for the moment.
And the first case, you presumably can do the lens.
Okay, so the first case I should say that was already done just by hand, by Brini, Eynard, and Marine. So this lens spaces case and invariants of basic knot in lens spaces are basically torus knot invariants in the 3 sphere.
So are the coefficients in the boundary of the Newton polygon products of cyclotonic polynomials?
Yes, yeah.
Just like the A polynomial.
And the coefficients have, so I say there's u, the coefficients on the boundary of Newton polygon. They are just monomials in the variable exponential of minus chi orb u divided by 2a sigma, where a is the LCM of A1 AR. So it's a monomial, so those things are monomials in exponential of u, maybe divided by some integer.
So the sums of these monomials are products, of cyclotomic polynomials?
I think, if I remember correctly. We can check that after. Because that we have then for all cases very explicitly. So there is a consequence of this result for knot theory, which is the question of, we have perturbative invariants which are, if I just pick up a coefficient in the expansion of H bar, I see a power series in mu, which is n times H bar. You can ask the question, is it the expansion at u equals 0 of an analytic function? For the FGs and rational homology spheres, this is a theorem that this series, independently of G, has a finite non-zero radius of convergence. That's due to Stavros, I think, maybe Marcos Marino, and maybe Tangley. I'm not sure if you know. So, but you still don't know what kind of analytic function, what are the singularities of this analytic function. So since here we can compute them by this topological recursion, which is a nice form, we can deduce some analytic property in U of this invariance. So I would like to introduce the notion of an Almos theorem. And I'll explain why after. And then there will be a theorem in the S3 divided by the P even case. That all basic knots perturbative invariants are in Q2. So first it should be Q power series in U, but they actually upgrade to Q, so a rational function of some variable kappa of U, and maybe a central, maybe another extension by some kappa 2 depending on kappa of U, where kappa of U is an algebraic function of this variable C, which depends on U, and kappa 2 is an algebraic function of kappa. So now come to the explicit example, which is new compared to the next one after the length spaces. So I will write what is a spectral curve, but instead of writing it as a polynomial, I will just write it because G is 0 in a parametric form. So the spectral curve is x of z.
Not
Z to the
confused
P.
by the notation.
Sorry?
You're using D both for the ADE classification, but it's also dihedral.
I know there are many
So-
symmetric groups. That's the dihedral group.
It's the dihedral group. I mean, here you wrote P plus 2, now you're writing P.
Oh.
It's a little confusing.
Okay. it's
What
because-
order dihedral group is it?
So when there's an exponential fiber of 2 to P, that's dP plus 2 in the label.
Meaning of order 2 times P plus 2.
Yes. So this is the form of the spectral curve. And kappa, so this one, kappa of U, solve the following equation. 1 plus 2 kappa to the power 1 plus 1 over P divided by 1 plus kappa squared is equal to C, this variable, which in that case is exponential of minus 2 divided by 4p squared sigma. And kappa 2, so maybe I can just erase that here. And kappa 2 is a function of an algebraic function of kappa, and this is this one. Square root. So this is what comes when you do this sum of residue in topological recursion, and this type of algebraic function comes in. So, modulo the remark that was before, here we have that for basic knots. If we had that for all conjugacy classes, if that was living in the same ring, that would mean that all perturbative invariants of any link in that manifold would live in this ring, using the scaling theory. So in a sense, that ring should be, so that's, but that's a conjecture, should be an invariant of the ambient 3 manifold, a non-trivial invariant. So that's the value for, that's what this ring is for S3 divided by TP. So I will make the conjecture that for any of those cases, the ring in which the perturbative invariant lives as analytic functions of U is an invariant of the ambient 3 manifold. So that's So maybe just a remark to say how do you recover perturbative invariant, at least in the simplest case, from this spectral curve. In that case, imagine you want to compute the HOMFLY PT polynomial, and the leading order when n goes to 0, h bar goes to n goes to infinity, or h bar goes to 0. For the knot K2, going along the fiber of order 2 in this S3 divided by n. That would just be given by the residue when z goes to, I think it's kappa minus 2 of p of log of minus y, and I think this is dx minus 1/2, minus p over 2, and x p over 2. So you can compute this residue here. You would find a hypergeometric form, a terminating hypergeometric formula for that. So in general, planar limit of perturbative. So planar means n goes to infinity. Invariants will begin by a sum of 2 terminating hypergeometric. We just come from expanding rho and computing Puiseux expansion of this y, this log of y at various points to the perturbative function of kappa minus 2. And this generalizes the planar limit of the Rosso-Jones formula for torus knots. There's only one hypergeometric. So if you want the true HOMFLY of torus knots in the sphere, it's a Q hypergeometric. If you study the planar limit, you just get the normal hypergeometric. And here we have a sum of 2 terms. But we don't know how to get to the full HOMFLY. So in the remaining time, which I don't know how much it is, in 20 minutes or?
Yeah, you have 12 minutes.
12? Okay. So I want to explain a bit where those results come from. And everything comes from the fact that these manifolds are very special, and the Chern Simons partition function can actually be evaluated. So this is either by using, so they have a simple social representation and a simple link. And in that way, Marigno derives a matrix model for this Chern Simons partition function. But you can also do the same thing in the context of Constellation integral, and that's what's actually done by Barata. The two computations gives similar results. It gives the same result but in different languages. There's another way to get it. Since you have manifold with the S1 action, you can do kind of localization techniques. And that was the approach of, I think, Bisley, several people, and Witten. There was also a paper of Kalin, and papers of Blau and Thompson on this cycle spaces. At the end, you arrive to the same type of results, which is that you arrive to the Chern Simons partition function as an integral over the Cartan subalgebra of G. So the measure takes the following form. It's a product. So here the Cartan subalgebra is identified with Rn. So I just take T1, Tn coordinates on this Rn, and we take the following measure. Product of dTi, there is a Gaussian wave, minus Tn Ti squared divided by 2 U0, where U0 is U divided by sigma, the geometric invariant of Seifert spaces. And here there's a product over all positive roots of the group of alpha t divided by 2 to the power 2 minus r, and then the product of the same thing, but taking into account rescaling by the order of exceptional fibers. So sine h of alpha t divided by 2am. So this is a kind of matrix model. And Zn, so if I call that d mu, the Chern Simons partition function is up to a correction factor here. So there's a Cn, which is known. It's the integral of d mu. And if you want to know what is VRG, it's the expectation value of the Jul polynomial in R in the variable. So that's, if you do that for the knot along the fiber of order AI, that will be Jul of the variables exponential of T1 over AI, exponential of Tn over AI, divided by the partition function. So you reduce everything to a finite dimensional integral. As I told you before, initially those invariants are defined as formal series in H bar and U. You can always use the formula to define formal series. But you learn more than that. You learn that this is actually a function of n, which is an integer, and that this is well defined when you integrate over Rn when u0 is positive. So if you want to derive results about analyticity of perturbative invariants, you need to study the large n asymptotics, not only as formal series, but asymptotic expansion. For a fixed value of u starting positive of those quantities. And then when you have an expression which is valid for all u positive, you will have to check that it's real analytic on the positive real line, and then try to analytically extend it in a complex plane. And then you will see where are singularities and so on. So there is a general theory to first address the all-order asymptotic expansion of those type of models, and then prove that it's computed by topological recursion. So it's a consequence of two works. First, the work I did with Thursdsay and Thursdsay of last year, which ensures that Zn has an expansion of this form. Asymptotic expansion, not formal. This is not just reduced to the perturbative arguments of before. Where Fg will be smooth function of u actually real analytic on the positive real line. And that omega n, which here are the expectation values of product of traces. So omega n of x1, xk, product of xj minus exponential of t over a trace, and I want the connected observables. And t is the matrix exponential of, so it's the matrix t1, diagonal matrix t1 tn. So those generate, I erased it, they generate the basic knot invariance when you the basic knot invariance when you expand xj goes to infinity. You have for all the basic knots you have there. And that has an expansion of this form, asymptotic. Omega n depending on n variables, and here's 2 minus 2g minus n, omega n g. Okay. The second thing is that once you know there is an asymptotic expansion like that, you can apply another thing, which is the work we did with Eynard and Bertrand, which say that these omega and g are indeed computed by the topological recursion. For the initial data, which is the spectral curve is y equals omega 1, 0 of x, and you need to know omega 2, 0 of x1, x2. And then you apply the residue formula that Bertrand showed to get those coefficients. So then the only matter, in which I would say in that case is a difficult point, is to be able to compute the spectral curve and omega 2, 0. I will not explain in detail how you do that, but I will explain to what the problem boils down and try to explain why you get some root systems in the star. When you want to study the asymptotic extension of that, first you look at what's the large n limit. And for that you need to understand what's the dominant configuration of T's which maximizes this width. So what you can first prove is that for chi orb non-negative, you can prove that the empirical measure of Ti, which is a probability measure whose your Dirac masses at those points sampled against this measure, converges to some distribution which maximizes this width. Well, that's an expectation, and also almost true. And then omega 1, 0, just by constructions, the large limit of trace of x over x minus exponential of t over a, omega 1, 0 of x is the Stiglitz transform of this mu f. So since mu x satisfies a maximization problem, there is a saddle point equation for mu x, which turns to be equivalent to a functional linear relation for omega 1, 0, which is of this form. So first, mu x is supported on a segment, which is by symmetry of the form 1 over gamma gamma, a segment of the actually in the way I wrote it, it's minus gamma gamma. Okay, and if I define a gamma prime, which is exponential of gamma over a, in the same change of variable, then for all x, the saddle point equation for W, say that for all x in gamma prime minus 1 gamma prime, if you look at the value of W10 above the cut plus the value below the cut, so this function, because you integrate over this segment, is holomorphic when x is in the complex plane minus this gamma prime minus 1 gamma prime. So come on this discontinuity from above or from below, sum the two contributions. The value of omega 1, 0 is related to the value somewhere else. So you have 2 minus r sum from L equals 1 to a of rotations of order a of W10 plus sum of all the orders of other roots. So from n equals 1 to r, from n equals 1 to a over am minus 1, and rotations of order a divided by am, mx, equal to, well, you have some right hand side. So you have to solve this type of equation. One way to do it is to try to do analytic continuation. If I'm here and I want to go further analytically, I can always define what is the value further by saying that, okay, that is equal to minus all the things that I put in the right hand side, and now this is well defined. So you can do something like that. You start with a function of the cut here, and when you go across the cut, you're going in some other sheet. So I continue here, and you define the value of the function here by that minus all this part. But because your rotations here, this function has cut on this segment, so this function now will have cut on rotation of this segment. So you create some new cuts here. So you can try to continue. What happens when I go there? I create a new sheet and maybe some other cuts. Okay. So at the end, you hope that this will close. There will be only a finite number of sheets. This is not in general true. But what happens, what you can look for is, does there exist V, which is an integer vector, so that the symmetrization of the omega 1, 0, from 0 to sum of all roots of unity of order A, let's call that Y. Can you find a VL so that this now closes when you do analytic continuation?
How do you know that you never reach natural boundaries?
What do you mean natural boundaries?
A circle beyond which it cannot be analytical.
So you see that here, well, the logs here are not very important, you can just get rid of them. So what's important is the left-hand side, the form of this thing. When you continue, you always find a function which has expression in terms of omega 1, 0 of certain rotations. And that has the same, that you know what's the analytic structure of that, it's that one. So we're in the case where the gamma group here is finite. So you never reach a natural boundary.
I see.
So to conclude, you can find in that way that for all chi orbs positive, there is a vector that, and you can actually find out what are exactly the vectors so that this transition sheets becomes a finite number. So y of x, yv of x is algebraic. And from there, once you have an algebraic function, you can compute the Newton polygon, you have a polynomial equation, and so on. If chi orb is negative, you can also prove that it will never be algebraic. So if there is a spectral curve for chi orb negative, it will never be polynomial of exponential x exponential y equals 0, which is another information we get. And when you really study the dynamic of sheets there, you see that they come naturally in, they're indexed by quotients of Cayley group. And that's how you see some root system appear. You just have to then read the classification of finite root systems. So I think I should stop. Thanks.
Questions or comments?
Well, in the negative Euler casuistic, does it mean somehow that one cannot apply the program, or? So
it means that so far, I'm not even sure if you would apply the program and if you knew the spectral curve that would give the correct answer. So the puzzle is the following. For chi orb negative, I do not know, because of this type of measure, I do not even know how to prove this as a limit when n goes to infinity. Because some convexity argument fails. So it means that I do not know if there exists a spectral curve, if this omega 1, 0 of x, and omega 1 of x. I do not know if it has a limit, it should have several limit points. And then, even though all the limit points are characterized by this saddle point equation, so they exist, but they can be finite, they can be many. But now, even if you start with that and try to solve this equation, you prove that the solution will never be algebraic. And which means that you do not know how to compute it in practice. So numerically, it seems that there exists a unique limit point. But so it just means that this limit point, you do not know how to compute it, more or less explicitly.
And what geometry does the three-manifold have in this case?
It's either hyperbolic or universal cover of PSL.
No, they're all Seifert fiber, but there are 5 geometries within the Seifert fiber.
Maybe nil.
No, nil is the, I think, the Euclidean case, the chi orb equals 0. I can check that.
Certainly it cannot be hyperbolic.
No, it's not hyperbolic, but there are several. I mean, there's.
No, I know this. Just I do not remember which one.
R2 cross R, for example, right? Or H2 cross R. So
I can check that. It's written somewhere.
Yeah. Okay.
So would you expect maybe in the negative Euler characteristic that you get a differential equation or maybe even a nonlinear differential equation?
So that's the characterization. Maybe there is a differential equation, but I wouldn't even know how to get it. It's more like going from monodromy representation to differential equation. That's a hard problem.
Like a
But also in a negative order characteristic, what it seems to indicate, because this will not be algebraic. So before I say that these coefficients of spectral curve would be algebraic functions of exponential of u, which in turn imply the basic knot invariants were also algebraic function, maybe with some extension of exponential of u. But in the hyperbolic, I mean this chi-orb negative, that may not be true. So the nature of the formal series might be different. But no clue so far what it could be.
Any more questions? Okay, the last time the speaker again.